Okay, so let's continue. So we start with general relativity. Now, the plan is to proceed this way. First, we'll study the dynamics of matter and radiation on curved space-time. We'll have to start with this because matter and radiation influence how the dynamics of space-time itself unfolds. So before we can get to the dynamics of space and time themselves, we'll have to study the dynamics of matter and radiation in space-time. By the way, cosmologists have a funny terminology, which is that radiation is matter. In cosmology, everything that's not gravity is called matter, even if it's light. Okay? Just like everything that's not hydrogen and helium is called a metal. In cosmology, that's just a simplifying terminology. Anyway, so the first step will be the dynamics of matter and radiation in curved space-time. Then we will study the energy and momentum that comes along with that matter, which is crucial because that will influence how space-time will evolve itself. So that's the three-step program there. So point one, the dynamics of matter on space-time. Remember that on a Riemannian or pseudo-Riemannian manifold, equations and equations of motion in particular can only be physically relevant if they're independent of the choice of chart. Cannot depend on what coordinates we choose. And this means that the equations of motion for matter have to be in terms of tensors and in terms of covariant operations, such as exterior, interior, derivatives, covariant derivatives, and so on. But in particular, for every kind of matter field, and that includes now light, remember, for every kind of matter field, there's got to be some field, some tensor field. So for every species of particles, such as electrons, quarks, gluons, pi mesons, photons, W bosons, and so on, there's got to be some species of field. Some tensor field will have to describe them. And we'll write it in this way, psi with a certain number of upper indices, a certain number of lower covariant indices, and the label I will label the species. So whether it's a photon or a gluon, for example. Now, in this way, we can easily treat photons and gluons, but fermions need a somewhat special treatment of spinors, and we will get back to spinors later on. It is actually possible to also identify spinors in the space of tensors, because this tensor space, which also includes the Grassmann algebra, can be equipped with yet another product, other than the Wedge product, a Clifford product, and then you have a Clifford algebra in which you can identify the spinors. But for now, let's just consider all species of particles as being described by some tensor field of fixed contravariant and covariant character. And we will get to the Dirac equation later on. Now, you may wonder, that's all fine. This allows us to describe all kinds of particles. And then we also have gravity, which is not described by a tensor. Gravity is described by the Christoffel symbols. And then you may wonder, maybe there's another force, just like gravity, out there too. Maybe we shouldn't just look out for carriers of the weak force, the W bosons, or the carriers of the strong force, the gluons, or the photons that carry the electromagnetic force. Maybe we should also look out for another kind of gravity force. Maybe there is another gravity there too, which might be much weaker than the gravity that we're used to. That's why it's not discovered yet. And it also is described by some affine connection gamma. Let's call it gamma tilde. How can we be sure that's ruled out? Because nobody's considering this. Why not? It turns out you can consider this. There might be an additional connection field. Let's call it a gamma tilde. There might be such a thing in nature, but it turns out that this doesn't mean that we have a second gravity. You see, if gamma is a connection field, and gamma tilde is a connection field, then the difference between the two is actually a tensor field, which is to say that it is completely equivalent to say either that there are two gravities, a gamma and a gamma tilde, or there is one gravity and an additional tensor field that describes the difference between the one gamma and the other. But why? Why is it that the difference between two affine connections is a tensor field? Well, remember, we can write down we can identify the character of a field by its transformation properties, and in this case, I mean, that's the physicist's way of doing it. In this case, that's the clearest. A Christoffel symbol transforms under change of charge in this way. Remember, this is the usual tensorial behavior, but then there is this non-tensorial behavior that doesn't even depend on gamma, which spoils the tensor character of the affine connection. And the same would be true then for another gravity, for another Christoffel symbol, gamma tilde. It too would transform in this way, but that means that the difference between the two would transform this way, because that term is identical for both cases. It doesn't depend on gamma. So that's identical, which means that the difference between the two affine connections would transform tensorially. So instead of having two gravities, we could say we have one gravity and another species of particle, which is one-fold contravariant and two-fold covariant. So in other words, we cover that case with what we considered earlier, simply matter fields that are tensorial. This observation has another important consequence. In order to derive equations of motion, we have to vary fields because, you know, the action is to be extremal. When we vary an affine connection, then we are considering a change in the affine connection. We're considering an affine connection to go from a gamma to a gamma tilde. So what we've just observed is that the variation of an affine connection is going to be tensorial. Okay? Whereas the affine connection itself is not, its derivative will be. Okay, so what are going to be the equations of motion of matter fields on a curved space-time? Now, as in special relativity, we require the action principle, which is to say that any theory of matter fields can be defined by specifying the so-called Lagrangian function L, which is to be a scalar function of the matter fields. Remember, contravariant indices, covariant indices, and this labels the species of particle. So the Lagrangian function is allowed to depend on all of the matter fields and also on their covariant derivatives. But we want the Lagrangian function L to be scalar. So eventually all the indices have to be contracted so that what comes out of this is a scalar. So overall, the Lagrangian of our theory will be a function of the matter fields and their covariant derivatives, and it will also include the metric in general, because all those indices need to be contracted. Then we can define the so-called action functional. So we take the Lagrangian, and remember, the Lagrangian is a scalar function. We multiply that with our metric-induced volume form, square root of g times the n form, which is the 4 form in space and time. And in total, this is then an n form. Remember, this is because square root of g d4 of x is a volume form. It's the metric-induced volume form. No, it's a top form. It's an n form, which is nowhere vanishing. And it's nowhere vanishing because the determinant, the absolute value of the determinant of g is nowhere vanishing because g is assumed non-degenerate. So here we have a 4 form multiplied with a 0 form. You could put a wedge here, but if you multiply with a 0 form, the wedge is the same as ordinary multiplication. So it's a scalar times a 4 form. It's a 4 form, and that's the kind of thing we can integrate over space. It will suffice to integrate that over some finite region in space-time, some bounded, closed, 4-dimensional region in space-time. You can choose it a few gazillion light years across. The physics locally cannot depend on what happens very far away. What we have now is a so-called functional. A functional is a map which takes as input functions, in this case the fields over space and time, all of the various species of particles fields, and the output is a number. So remember, a functional takes as input functions, and as output it gives you just a plain number. So you plug in those functions of space and time here, and then you integrate that over space, you get a number, that's the action functional. Then the action principle, or action postulate of classical physics is that in nature, physical fields psi are such that the action functional is extremal in the space of all fields psi. Of course, quantum mechanically, that's not quite true. But for now, we'll consider the classical theory. Quantum mechanically, of course, and that was the insight of Dirac. Dirac only hinted at it, but Feynman then really worked it out that really what's going on is that nature assigns to every field evolution technically a probability amplitude, and there are fluctuations around the extremal action. But in classical physics, the action principle simply says that the evolution of the matter fields psi is such that this equation holds, such that the action is extremal with respect to variations in the matter fields. But what exactly do we mean by that? Since it comes up quite a bit, I thought I'd go a little into detail what we mean by this functional derivative, because it's really not that mysterious. We can reduce it to an ordinary derivative. Okay, so that's the action principle. What does it mean actually? What's the definition of it? So the definition of this functional derivative is this. A variation, delta psi, of the matter fields in some region B is a one-parameter family of matter fields. It's a one-parameter deformation of the matter fields. And lambda will be the so-called deformation parameter. So psi of P, or psi of X, I mean, P is the point of the manifold. If you choose a coordinate system, you might call it X, but without it, it's just psi of the points of the manifold. That would be the ordinary matter fields, but as functions of space and time, functions of the point in the manifold. But we now vary those matter fields with a variation parameter lambda, just some parameter, a real number lambda, in some finite interval around 0, from minus epsilon to epsilon. And we choose the lambda, we require this one parameter variation or deformation of the matter field to be such that when we choose the deformation parameter lambda to be equal 0, we get back the original matter field, which we haven't changed, right? But if we choose the lambda to be not 0, then smoothly we are actually changing the matter field. For example, by having it grow larger amplitudes over here, smaller amplitudes over there. And the larger the lambda is over here, and the smaller the larger the lambda is over there. But such that if lambda goes to 0, you get back to the original matter field, whatever that was. Now we require of these variations, of these deformations of matter fields, to be such that they obey these two conditions here. One is that when the parameter lambda is 0, then we haven't done anything to the matter fields. We just leave them as they are. But when lambda is not equal to 0, then smoothly the matter field may be different. We do, however, require that there is no change in the matter field outside that finite region B, the region manifold without B. So outside of B, we don't want any modification to the matter field. On the boundary of the region B and beyond, we want the variation to vanish. So now, you see, you can write down your own deformations of a matter field. You write down a matter field, you choose an arbitrary matter field, and then you can define a variation of it by just making it now a matter field that depends not just on x and t, but also on lambda. Such that if lambda is equal to 0, you get your original matter field. Such that if lambda is not equal to 0, then you have a slightly modified matter field, or even strongly modified, but in any case smoothly modified matter field. But the modification has to be restricted to that finite region B, which you can choose arbitrarily large. Okay, so we have the overall manifold, and then we have a finite region B, and as we run through various values of lambda, in B, the given field may change, but only in B. And if lambda is equal to 0, we are not changing. Okay, and then we define the variation of psi to be, or this symbol, the del of psi, to be simply the ordinary derivative of the field with respect to lambda at lambda equal to 0. So that's how much it's changing with respect to lambda around the point of no change. Then the action principle says that the variation, or the rate of change of the action with respect to a change in that parameter, which is now an ordinary derivative, this is just an ordinary derivative here, is equal to 0 for all possible variations, all possible ways that you can parameterize changes in that physical field. So that's reducing it to ordinary derivatives. Now let's evaluate that. So the action principle is that the variation of the action with respect to the deformation parameter has to vanish for all possible variations. And this means, if we go back to what the action is, here it is. The action depends on the Lagrangian, and the Lagrangian depends on psi and its first covariant derivative. But not on its second or higher covariant derivatives, right? It's just like in classical mechanics. The Hamiltonian and the Lagrangian depend on the amplitude and the first derivative, position and momentum, but not on the acceleration. Because we want the equations of motion to be of second order, not higher. Okay, so we evaluate this now. And what do we get? We have to differentiate the action with respect to lambda. So the action is this integral here. And we have a sum over all species. That's the summation over I. And then the Lagrangian in the action integral depends on both psi and on the covariant derivatives of psi, the matter fields. So we have to differentiate the Lagrangian with respect to the matter fields, and then differentiate the matter fields with respect to lambda. So this is really just d psi by d lambda. Remember that we have this. D psi by d lambda is by definition written in this way. So this was just the chain rule here. You're just saying dl by d psi by d lambda, chain rule. And d psi by d lambda is also written in this suggestive way. It's just the notation for it. Okay, so that's the first term. And then we get a second term where we differentiate the Lagrangian with respect to the occurrences of the covariant derivatives of the matter field. And then we have to differentiate the covariant derivatives with respect to lambda. So this is really the covariant derivative of psi by d lambda, which again, by the terminology, by the notation earlier, we can write as the delta of psi covariant derivative of psi. And we just carry this forward here, the square root of g from the volume form. The metric does not depend on lambda, so we don't have to differentiate it. Now let's consider those two terms separately. Particular term 2, you've probably all done calculations like that. Maybe not for general relativity, but generally you must have seen Euler-Lagrange equations, and you know that at this point, what you want to do is the integration by parts. Because we have here delta, not of psi, but delta of the derivative of psi. Here we have a delta of psi. If we could throw this covariant derivative on that side, it would be fine, because then we just have a delta psi here, and we can collect the terms that multiply the delta psi and read off the Euler-Lagrange equations. So we need something like integration by parts now. Let's see.
Why don't you vary with respect to g?
Oh, we will do that later. But at the moment, we want to know the equations of motion for the matter fields. And for that purpose, we have to do the variation of the action with respect to the matter fields and set that equal to 0. And later on, for gravity, we will vary with respect to the metric. So we will do it, but later. You know, for whatever degree of freedom you want to know the Euler-Lagrange equations, the equations of motion, for that degree of freedom, you have to do the derivative. Okay, so the second term, the one where we want to do the covariant derivative. So what we have is the variation of the covariant derivative of psi. But this is actually the covariant derivative of the variation of psi. Now here at this point we use for the first time, I think for the first time, an argument that we will see come up quite often. Why is it that we can interchange here that variation with that covariant derivative? Well, remember that in a geodesic coordinate system, at the origin of a geodesic coordinate system, that is to say in Riemann normal coordinates at the origin, the covariant derivative is the ordinary derivative. Because at the origin of a Riemann normal coordinate system, the Christoffel symbol is vanishing. Okay? So let us look at this equation here at the origin of a Riemann normal coordinate system. At the origin of a Riemann normal coordinate system, this equation is the same equation without the semicolon, just replacing the semicolons by ordinary commas. It's just ordinary derivatives. Then let's ask, is it true? If we put ordinary derivatives there at the origin of a Riemann normal coordinate system. And there, yes, it is true. And it is true because this variation is really a derivative, an ordinary calculus Newton-Leibniz derivative with respect to lambda. This, if it's a comma, is just an ordinary derivative in the direction of xe. And then this equation is simply expressing the interchangeability of two ordinary derivatives. Okay? So what we see here is that this equation holds at the origin of a Riemann normal coordinate system, where the comma is the semicolon. Now, since it's true with the commas at the origin of a Riemann normal coordinate system, it is also true with the semicolon, because the gamma is actually 0 there anyway. But then we can conclude that this covariant equation is true at the origin of a Riemann normal coordinate system. And now it no longer depends on being at the origin of a Riemann normal coordinate system. We can now conclude that this is true in any coordinate system at any point, because any point can be chosen to be the origin of a Riemann normal coordinate system, so we can go through this argument everywhere. So the overall logic was going to the origin of a Riemann normal coordinate system where you're dealing with ordinary derivatives. If the equation holds there, you can make it semicolons. And then you can lift it and say it doesn't depend on where and what coordinate system. It's always true. You will see this come up several times. Okay, so we can exchange them, which means that the second term now from above takes this form. Remember, we are dealing with this. The overall variation of the action, we had this term here and we have this term. In this term, we just established that we can interchange the covariant differentiation with the differentiation with respect to lambda. So what we have is that the second term is given by this expression here, where we are now varying first, so differentiate first with respect to lambda, and then we do the covariant derivative, which is the opposite sequence from what we started out with. But then we can actually do the integration by parts. Now, how does that work on curved space, integration by parts? See, here we have a function times the covariant derivative. And we can write this term here in this way. Let's take the product of this and that. That's what I wrote here. Just the product of those two. And then I covariant differentiate the product of the two. Okay? Tensor contracted with another tensor. And I have covariant derivative outside the bracket now. Remember that the covariant derivative is a derivation. Even though it is highly non-trivial, it obeys the Leibniz rule, which is to say that this expression, covariantly differentiated, gives us two terms. One term where we differentiate covariantly this term and leave that the same, and another term where we leave this the same and covariantly differentiate that. That second term is what we have here, right? Leaving this the same and covariantly differentiating that term. But this is overkill, right? We get two terms. The covariant derivative of this product gives us this term plus a term where that one is differentiated and this one carried forward. So we have to subtract that term, and that's what I do here. This is the term where we covariantly differentiate the first term and leave the second the same. Okay, so we write this as this total covariant derivative minus that other term. You see that this is, in effect, integration by parts. Because that is going to be a boundary term, because it's a covariant derivative of some vector, ke. See, the whole thing contracts just to leave one index over, and that's contracted here. That's going to be a divergence. And it's going to be a boundary term that, as we will soon see, goes away. And we're left just with this term, which is very similar to that one, except that now the covariant derivative, which used to be here, is going to be there. See? It's going to be here. And that's what we wanted. Get rid of the covariant derivative on the variation and throw it instead onto the left-hand side. Okay, so remember we call this whole thing here a vector field ke. So this overall term, which we will now argue is a vanishing boundary term, is going to be ke covariantly differentiated with respect to E and contracted, square root of G, and so on. Now this is actually the expression for a divergence. You know that from flat space, if you take a vector field and you want to calculate its divergence, you simply take ke and then comma E. and then times d4x, and that's the divergence, right? Now, to show that in the covariant case, in the curved spacetime case, this is also the divergence, I leave you here with a little exercise to show that. You have all the ingredients already in the notes. What you have to use, though, is that the volume form in question is the metric volume form. So you can show that for all vector fields psi, when you take psi mu, semicolon mu, times the volume form, then this is the divergence of the vector field psi with respect to the volume form omega, if, and that's important, if the volume form is the one induced by the metric, square root of g times dx1 wedge, etc. to dxn. In the proof, you need to use, I mean, it's really just 3 lines, and in the break I can show you how to do it if you want to see. You need to use that the covariant derivative of the metric is vanishing. So it's really only true if the volume form is the one that arises from the metric. Okay, so what we have is that this term here, this term that we want to identify as a boundary term, is really the divergence of the vector field k, k being this whole thing. Okay, and remember, here's the sum over all species. Now, let's use Gauss's theorem. Remember that the divergence of a vector field is also the Lie derivative of the volume form in the direction of the vector field. I hope it's already in our formula collection. It's one of the important formulas that one can easily forget. And this you should really remember, the Lie derivative is the anti-commutator of the inner derivation and the outer derivation. Right? So the Lie derivative is I after d plus d after I on the volume form. Now the volume form is top degree. It's an n form, which means that when the d acts on it, you get a 0. So the Lie derivative acting on a volume form is only this. But you see, that's great, because that gives us a d of something. So we're integrating over a volume the d of something, namely the d of the inner derivation of omega. And that is Gauss's theorem. So this integral over the divergence is simply that integral here. I'm just reminding you of a calculation that we did earlier, namely that whenever you have an integral over divergence, it is really the integral over the boundary over just the inner derivation applied to the volume form. Right, but this vector field k that we have here, this vector field k is proportional to delta psi, to the variation of psi. You see, k is proportional, in particular, it has some other stuff, but it's proportional to the variation of the matter fields. And remember that we chose our variations to vanish at the boundary of the region B and beyond, which means that the vector field vanishes at the boundary and beyond. But here we're integrating over something that's proportional to the vector field at the boundary, so it's vanishing. So indeed, the boundary term vanishes, and that means that the second term simplifies. It's only one term left over, and the overall total derivative now of the action with respect to lambda, so the first variational derivative of the action, is then given by the first term that we haven't changed at all. Remember, that's the term where we differentiate the Lagrangian with respect to the matter fields, and then we have the delta of the matter fields, and then the second term that we just operated on and did the integration by parts. And here we have, again, just the variation of the matter fields, not any derivatives of it. And here we have the covariant derivative and a minus sign from the what was effectively an integration by parts. Now we can collect this and that term, because both are multiplying the same thing. And the equation that this is all vanishing has to hold for all variations of psi, which is to say that in the function space, the sum of this and that term is orthogonal to all vectors delta psi, and therefore the sum of the two has to vanish. And this is the Euler-Lagrange equations of the matter fields. So you have to differentiate the Lagrangian with respect to each one of the matter fields, then take minus the derivative of the Lagrangian with respect to the covariant derivatives of the matter fields, which you then have to covariantly differentiate again. In this way, we obtain a lot of equations for every species of field I, and every choice of its indices, we get another equation, and together these are all the equations of motion of matter. Let's consider an example. Let's say a real-valued scalar field. Such fields can describe, for example, pi mesons or the inflaton particle. That, as we will later see, is very important in cosmology. Or it could be a Higgs. I mean, there are a few candidates for scalar fields in nature. The pi meson is not a fundamental particle. It is composed of a quark and an interquark, but the Higgs is considered to be fundamental or not divisible, to be really elementary, and so also the inflaton is considered to be really elementary. Then what could be the Lagrangian for a real-valued scalar field? Well, we could choose, well, the way to determine it is to appeal to the equivalence principle. So we choose a geodesic coordinate system where, at its origin, in the neighborhood of the origin, special relativity is supposed to hold. And when we do that, we obtain for the Lagrangian of a scalar field this expression, because this is the Lagrangian of a scalar field with the semicolons replaced by ordinary commas in special relativity. You know, it's just d mu psi, d nu psi, g mu nu. But at the origin of a Riemann normal coordinate system, if they are true with commas, it's also true with semicolons, because the difference is a gamma, and the gamma is vanishing at the origin of a Riemann normal coordinate system. So at the origin of a Riemann normal coordinate system, that Lagrangian is the correct Lagrangian with or without semicolon. If we put it with a semicolon, now it's a covariant equation, and that generalizes to curved space-time. So then the Euler-Lagrange equation that you obtain from that Lagrangian using our expression above is this one, and I leave it to you as an exercise to verify that this is how you can write it. Of course, you've seen it and you've done this Klein-Gordon equation before, I assume, but maybe the notation is new. So this means second covariant derivative. That gives us the Klein-Gordon equation. Another example is electromagnetic fields. Assume that there are no charges. So let's look at just the free electromagnetic field. So there are only electromagnetic waves. We will later couple electromagnetism to matter fields, to charges, but for now let's consider electromagnetism alone. But then we define the electromagnetic 4 potential as a real number valued one form A. That's the vector potential of electromagnetism. It's a one form A, so it's really just a cotangent vector field. And then we define the field strength tensor to be its exterior derivative. So A is a one form, dA is a two form field strength tensor. So it's a covariant, antisymmetric two tensor. And maybe you remember, I spelled it out a few lectures ago, how that looks like, this F. It's a 4x4 matrix which has the E fields and the B fields on its off-diagonal, in its off-diagonal elements. Then the Lagrangian of electromagnetism can again be inferred by using the equivalence principle and by using that we know how the Lagrangian of electromagnetism looks like in Minkowski space. And this is the Lagrangian. And the only difference to Minkowski space is that we are using here the proper metric instead of just the eta of Minkowski space in Cartesian coordinates. Then, again, if we apply the Euler-Lagrange equations, we vary with respect to A, the Euler-Lagrange equations become these. Now, if you remember, this equation we had before, because we considered the free electromagnetism before, a few lectures ago. So we had this equation earlier, and we identified it as the equation that the co-derivative of f is equal to 0. What you can also prove is that this equation holds true. These covariant derivatives of the f's with cyclically changing arrangements of the indices. But this is not an Euler-Lagrange equation. This is simply the statement that df is equal to 0. Remember that f was dA, t squared is 0, so that was a condition that that was an equation that arises simply from the definition of the field strength tensor, because the field strength tensor is an exact form, right? F is the d of something, so it's exact, and that implies always that it is closed. The other way around, it's not guaranteed. It depends on the connectivity properties of the space-time. But at this point, you may be wondering, wait a moment. Our equations didn't look exactly like that. This one we had exactly like this. And also this one we had like this. But our equations didn't exactly look like that. Because if you remember, actually this one we had, but this one we didn't have. This equation looked different. If you spell this out in the original way as we had it a few lectures back, you get this equation but with commas, not with semicolons. I think we even did the equation before we had the covariant derivative. So we had this equation with commas instead of semicolons. And obviously it's a different equation with the semicolons, because then you get plenty of gammas involved. But, and here we can use the same magical argument as before. I shouldn't say magical because it's really true. This equation actually holds true with or without commas. Originally, if you just view it as arising from differential forms, then you just have commas here, arising from the derivatives that come from the exterior derivatives. But then we know that it's a covariant equation with the commas. If we look at it at the origin of a Riemann normal coordinate system, then this equation will hold, because it holds in any coordinate system with the commas. But at the origin of Riemann normal coordinate system, the gammas are vanishing, and therefore we can turn the commas into semicolons. But then it's a covariant equation. It must hold in whatever coordinate system. So this equation is actually true for semicolons and for commas. Now let's couple electromagnetism to a scalar field. We don't do spinors just yet, so let's just couple electromagnetism to a charged scalar field. For example, pi plus or pi minus mesons would describe charged scalar fields. And then how do we couple them to electromagnetism? Well, if you've done electromagnetism special relativistically, then you know that this is the Lagrangian of electromagnetism coupled to a charged scalar field. Here we have the action of electromagnetism alone. It was just a contraction of two field strength tensors. We had that a few slides up. This is the mass term of a charged scalar field. It's charged because it has a complex conjugation in it. It's a complex field. A real scalar field does not carry charge. And it really goes beyond the scope of this course to discuss that, but I've put it here, the explanation for why, in case you're interested, the explanation for why it is that only complex scalar fields can be charged. Okay, so for a charged scalar field, we have, is this too loud? Should I close the door? No, it's okay. Let me know if it's getting too loud. Oh, thanks. Okay, so this is the mass term for a charged scalar field. Then, if there was no coupling to electromagnetism, then this is simply the kinetic term of a charged scalar field, you know, the covariant derivative of psi star, covariant derivative of psi, and then you contract it with the metric. But in the presence of electromagnetism, the covariant derivative gets extended to include also the gauge field of electromagnetism. Remember, this is now doubly covariant derivative. It's a covariant derivative with respect to the metric, but also there is this additional term here which couples the charged scalar field to the electromagnetic field, where indeed the A play the role of an affine connection. Just like in here, the gammas play the role of the affine connection describing gravity. This is a different kind of affine connection which describes electromagnetism. In any case, the point is that you can take this equation from special relativity, where it simply has commas, and then wherever you find a comma, make a semicolon by the usual argument of going to the origin of a Riemann normal coordinate system, where you can go from a comma to a semicolon without changing anything, because there the gamma is vanishing. And then you have a covariant equation which automatically holds in any coordinate system. Okay, so that gives you then the Lagrangian for electromagnetism coupled to a charged scalar field. So we have two species of particles here, the psi and the A, and we have two equations of motion. We have two Euler-Lagrange equations. We can do the variation with respect to the psi, and we can do the variation with respect to the A. If we vary with respect to the psi, or the psi star, it doesn't matter, you get the same equation up to complex conjugation of the whole thing. If we vary this equation with respect to psi star, then, okay, so you vary this equation with respect to psi star, so you have to do the functional derivative with respect to psi star, and with respect to covariant derivatives of the psi star. Then this is the equation that you get. Again, I leave it to you to actually plug it in and verify that this is what you get. And you see that it is the Klein-Gordon equation. It's the second derivative. This is the D'Alembert acting on psi. Second derivative of psi, here's the mass term, m squared psi. And if there was no electromagnetic field, then all those terms with the A in them would vanish, and it would be just equal to 0. So Klein-Gordon equation term equal to 0. But with the electromagnetism, we have those extra terms in here. So this is how psi is affected by the presence of electromagnetism. If we vary it instead with respect to psi, then we would get the exact same equation up to a complex conjugation of the whole thing. So it's really the same equation. On the other hand, the other species involved in this is electromagnetism. It's the photons. We can also vary the action with respect to A. There you go. We can vary that action with respect to A. And remember, there's an A inside the F as well. then we obtain this equation of motion for electromagnetism. This would be the Maxwell equations in the absence of, this equal to 0 would be the Maxwell equations in the absence of any matter. But with the matter field around, with the charged field around, we get these additional terms. Try it out. Now, let's look into the Dirac equation. This will be an instance where we can really benefit from having put in all this hard work early on, where we gave ourselves the freedom to choose bases in the tangent and cotangent spaces whichever way we want, not necessarily related to the coordinate system that we use. And here's why. In special relativity, this is how the Dirac equation looks like. Right? Here we have the first derivatives, and they are contracted with the gamma matrices. Anyway, historically, Dirac tried with the second derivatives. The Klein-Gordon equation came earlier than the Dirac equation. But they soon figured out that the Klein-Gordon equation has a problem because there were not just positive but also negative energy solutions. And Dirac traced that back to the fact that there were second time derivatives in there. See, the time derivatives are basically the energy. And so when you have the second time derivative, you have energy squared, which means that for any positive energy solution, there's going to be a negative energy solution. So Dirac said we can only solve that problem by going to first order. It didn't solve the problem at all, and he ended up predicting antiparticles as the explanation for why they are negative energy solutions. But the quest to find an equation that is first order in time still paid off. So Dirac was facing the problem that he wanted to write down a first order differential equation in time for relativistic fields. But when you have only first derivatives in time, you can also only have first derivatives in space. Otherwise, how could he possibly be covariant? But then, when you have this bunch of derivatives, of first derivatives, how can you get an expression that you can then have act on wave functions? You see, you need to contract it with something, but there is no canonical vector field that you could contract with. So he invented one, and that's the gamma mu's. And he invented the gamma mu's such that the equation came out covariant. The psi of x is a Dirac 4 spinner. This is now for 3 + 1 dimensional space-time. It has 4 components, psi 1 to psi 4. And Dirac figured out that the gamma matrices, the gammas have to be matrices that obey these anti-commutation relations. For 2 reasons. One was that they had to obey commutation relations that are covariant, so that fixed it to something closing into the metric. And also, they had to be this particular combination, so that when you square this expression, this Dirac equation simplifies and it becomes the Klein-Gordon equation for each component. So the Dirac equation is specifically chosen such that each component of the Dirac spinner actually obeys the Klein-Gordon equation. Let's verify that. This is the Klein-Gordon equation. This is the Dirac equation, just this much. That's the Dirac equation. Now, if this applied to psi is equal to 0, then you are free to multiply here with whatever you want, and it's still equal to 0, right? So if this acting on that is 0, then you can multiply here with 27 or whatever comes to mind, such as this expression. So we multiply that expression from the left, and it's still equal to 0. But if we do that, if we multiply this onto that, let's bracket this way. And we obtain 4 terms. We obtain a term where we have gamma nu, and the 2 derivatives. That's this term. And then we get 2 mixed terms, where we have this times the m, and the m times that. And we have a term with m squared. Overall, 4 terms. Now, let's collect these terms. And then what we observe here is that these 2 derivatives are symmetric. I mean, it doesn't matter whether you write d nu or d nu d mu. The middle 2 terms cancel each other because we've chosen the sign here to be opposite of the sign there. That just means that the middle term vanishes. And now we have an expression here that almost looks like the Klein-Gordon equation. We have second derivatives, and we have the mass squared term, almost like the Klein-Gordon equation, except that this is not quite matching the Klein-Gordon equation yet. Now, but Dirac at this point was still free to choose the gamma matrices whichever way. So, and he didn't even know what dimension they should have yet. So what he said is, let's choose the product of the gamma mu and the gamma nu in such a way that this thing boils down to just the D'Alembert operator, just the second covariant derivatives. Now, the product of those 2 has a symmetric and an antisymmetric part. Every matrix has a symmetric, can be decomposed into a symmetric and antisymmetric part. The antisymmetric part doesn't matter, because the antisymmetric part would be going away because this part is symmetric. You contract them, so would go away. So therefore, let's look at the symmetric part in here. The symmetric component of this product is this. It's just the symmetric product, the sum of the 2 permutations of it with 1/2, just the symmetric part of it. And then what we require is that this symmetric part is what is needed to make the whole thing the D'Alembert operator. So what we need here is that this symmetric part is just the identity matrix times eta mu nu, and then here we have the second derivatives. So this is how Dirac arrived at the Klein-Gordon equation. He said we can get away with requiring this equation for spinors if those matrices here obey these commutation relations or these anti-commutation relations. Because then every component of this equation is actually the Klein-Gordon equation and therefore covariant. He should have realized at this point that he's not going to solve the negative energy problem, right? Yes?
Why does he require that every component?
Oh, just for covariance. There's no other equation that you can have covariant second order. The only covariant second order differential operator on scalars is the Klein-Gordon, is the D'Alembert operator. Okay, so now in general relativity, what can we do? You see, if you look at the Dirac equation, then remember the deal was, yes, this equation is covariant if you can find matrices gamma that obey this. But what on curved space? In curved space-time, the matrix can take any form, can be very complicated. If we went that route, then it seems that at every point in space-time, we have to find a new set of gamma matrices that obeys the new anti-commutation relations. That would be incredibly tedious. It's just not feasible. However, what we can do with all this hard work that we did earlier is to choose a basis in the tangent and cotangent spaces such that actually the metric takes the form of eta mu nu everywhere. And when we do that, then we need only one set of gamma matrices to express the Dirac equation everywhere. Okay, so in general relativity, we choose an orthonormal tetrad. So we choose orthonormal set of cotangent vectors so that we achieve that the metric always takes this form. It's an earthquake. Actually, there was one, right? There was one in Afghanistan 10 hours ago. Maybe that's maybe just now it arrived.
What's the construction we heard earlier?
Or maybe it's that. Yeah. Okay, so we choose our basis such that the metric tensor always takes this form. I wonder if it's pressure or shear wave. Anyway, see, they arrive at different times. Okay, so that means that we can take the usual gamma matrices that we know from special relativity and work with them. So it should be easy. We simply say that the Dirac equation in curved space-time is given by the Dirac equation, where we now, instead of having the ordinary derivatives, use the covariant derivatives, the semicolons, or just the covariant derivative symbol here. Right? So it's the nabla, the covariant derivative in the direction of E mu. There's just one problem. This here is a spinor field, which means that we don't know yet how the covariant derivative is acting on that. Remember that we defined what the affine connection does for tangent vectors, then we inferred what it does to cotangent vectors, and then we inferred what it does to any tensors. But what does it do to a spinor? We haven't determined yet how the covariant derivative acts on a spinor. We'll have to determine that, and then we can write down the Dirac equation. Now, all of this could be done more abstractly, and I will say something about this later on, but I thought that since this might be quite new and alien to you, we'll do it the pedestrian way to make sure we get all the details. So what is the covariant derivative of a spinor? What is that? If this is some force spinor. Okay, as for preparation, let's remember something. The covariant derivative of a vector field gives us the infinitesimal Lorentz transformation by which this vector rotates under parallel transport. Okay? Remember that when you parallel transport a vector, then you're not going to change its length. This was built into general relativity when we decided that the affine connection and the metric have to be compatible with each other. The compatibility condition between the two was that the relative angles of two vectors are not changing as you parallel transport them, and neither does the length of a vector change as you parallel transport it. That gave us the relationship between the two. This allowed us to express the Christoffel symbol in terms of the metric, for example. So the length of a vector does not change as you parallel transport it. So the only way in which it can change, and this is, the change is what the covariant derivative is picking up, the only way that it can change is that it can rotate. But covariantly, a rotation is a Lorentz transformation. So therefore, what the affine connection gives you, what the covariant derivative gives you, is the infinitesimally small Lorentz transformation, or rotation, that a vector experiences as you parallel transport it infinitesimally. this should also already give you a hint as to what the affine connection is if it's not a tensor. You know, it's a one form, if you remember. You know, one of its lower indices can be interpreted as the index of a one form. But where does it take its values in? Well, it's an infinitesimal Lorentz transformation valued one form. Right? Because you plug in the direction in which you parallel transport, and out you get the matrix of an infinitesimal Lorentz transformation. So the affine connection is infinitesimal Lorentz transformation valued. It's an infinitesimal Lorentz transformation valued one form. Okay, so now the idea is to use this insight to calculate what the covariant derivative of a spinor is going to be. Namely, a spinor should be rotated by the same infinitesimal Lorentz transformation as any vector would be. Right? So you do a parallel transport. The affine connection tells you by what angle, so to speak, or by what Lorentz transformation, the vector is going to be rotated through the infinitesimal parallel transport. And then that very same Lorentz transformation will also rotate the spinor. Of course, for that, we need to know, how does the spinor rotate? How does a Lorentz transformation act on a spinor in special relativity? And then we can generalize that to general relativity. Okay, so let's say, I'm just spelling out in equations now what I said in words earlier. Let's say we have a tangent vector E rho, and when we then parallel transport it, so we move it infinitesimally in the direction of E mu, then it acquires a change of direction, which is given by this new vector here. It's the affine connection, right? It's to differentiate in the direction that you're moving, E mu, the vector E rho. And we can write this as an infinitesimal Lorentz transformation valued one form. Namely here, this is the connection one form. The connection one form is really the Christoffel symbol, right? It has one upper index and two lower indices, but one of the lower indices we suppressed. We call it a form. That's why it has a slot open where we can put in the direction vectors. So we put the direction vector in there. We want to parallel transport in the direction E mu. And out we get a matrix, namely this matrix here. And that's a matrix of infinitesimal Lorentz transformation. That is applied to our original vector, and that's how it's rotated. So this is an infinitesimal Lorentz transformation. We can also write it in this way, that our vector E rho, the original vector E rho, under infinitesimal parallel transport, goes into this infinitesimal Lorentz transformation acting on E rho, which is identity plus this infinitesimal generator of the infinitesimal Lorentz transformation. So the overall Lorentz transformation is the identity plus the infinitesimal part of it. So overall, this is a Lorentz transformation that's almost the identity. It's identity plus a little bit, where this little bit is given by this affine connection here. Okay, so what we've extracted here is the Lorentz transformation matrix that a vector experiences as it is parallel transported. And now let's dig into the knowledge of how spinors transform under Lorentz transformations, and then apply that Lorentz transformation to a spinor when it is being parallel transported in the same direction. By the way, if you lower that index, then you get antisymmetry here, which is, if you remember, the a hallmark of an infinitesimal generator. I'm adding here lots of comments, but just there are extra comments in case you're interested. Okay, so now that we know the infinitesimal Lorentz transformation for any infinitesimal parallel transport, the strategy is that we apply that same infinitesimal Lorentz transformation on spinors for the parallel transport of a spinor. Now, from special relativity, we now take how Lorentz transformations act on spinors. For that purpose, let us choose a basis in the space of spinors. So just like in the tangent space, we chose bases, we can choose bases in the spinor space as well. Spinors have 4 components. We need 4 basis vectors Si at every point in space and time. So our spinors can be written as coefficient functions times those basis vectors. So these are just number-valued functions, and these are spinors. Then the question is, how does such a spinor, such a basis spinor, behave under parallel transport? Just like we earlier, a few lectures ago, defined how the covariant derivative in one direction acts on a tangent vector, a basis tangent vector. Now we are studying how the covariant derivative acts on a basis spinor. This is analogous to this equation, right? So the covariant derivative of one tangent vector, of this tangent vector in the direction of that tangent vector is given by this, where this was the infinitesimal Lorentz transformation. Now we want to know how that works. You see, if we know what this is, then we can work out how the covariant derivative acts on any psi. Because if there are coefficient functions in front of those basis vectors, coefficient functions here, then by the Leibniz rule we can work out what we get. So now from special relativity, it is known, I hope you know, if not, I'll remind you now, it is known that under infinitesimal Lorentz transformations, which always take this form, right? Lorentz transformation is the identity plus some matrix of small Lorentz transformations. Then vectors transform like this. It's very consistent with what we just said, namely that the affine connection does exactly that as well. And this is the thing that I have to remind you of, and that may look a little frightening if you see it for the first time. In special relativity, when you have a spinor and you want to Lorentz transform it, then under an infinitesimal Lorentz transformation, the spinor goes into itself minus a quarter, and then this is the small change of Lorentz transformation. It's the small perturbation of the Lorentz transformation times this thing here, this 4x4 matrix acting on that spinor. Remember, it's much easier if we do a Lorentz transformation of a vector. We simply have this matrix contracting with a vector, but not so for spinors, as it should be, because spinors have their own space. That's a 4-dimensional space, and these guys are naturally acting on that space. So let's check this. We have a contraction of those matrices, of this matrix omega, with those so-called generators of Lorentz transformations in spinor space. I put here a box with a full explanation of how this comes about. Let me give you the gist of it. Remember that when you are dealing with a rotation, rotations are generated by angular momenta. If you exponentiate angular momentum operators, then you get rotations. And those angular momentum operators have a particular algebra. They have a particular set of commutation relations with another. Now, it turns out that the generalization of this to space-time, where it's not just rotations but Lorentz transformations, it works very similarly. We have certain commutation relations that generalized angular momenta are obeying. These commutation relations are really just the algebra, expressing the Lie algebra of the rotation group, or the Lorentz group. And it turns out that these commutation relations can be fulfilled not just by generalizations of the angular momentum, which is position times momentum minus momentum times position, if you remember this antisymmetric combination there. No, it turns out that those commutation relations also have a representation in terms of finite dimensional matrices, which correspond to half-integer spin, that cannot be represented through multiplication and differentiation operators. And the commutator of the gamma matrices gives you a representation of these commutation relations. You see, you have here for every choice of mu and every choice of nu, you have a 4x4 matrix. And all those 4x4 matrices obey the commutation relations together. They obey the commutation relations of the Lie algebra of the Lorentz group. So these guys are the generators of Lorentz transformations in their representation, which in this case is a spin 1/2 representation. It's a huge field, really, and I can't really do it justice in just a few minutes. Okay, so what we've seen now is that when you have a transformation that's a Lorentz transformation that's almost the identity, but it has an infinitesimal change, so you do an infinitesimal rotation, just like what you get when you do a infinitesimal parallel transport. Then this is the matrix of the infinitesimal Lorentz transformation, and a spinor is transforming under infinitesimal Lorentz transformations in this way. This is just special relativity, nothing to do with parallel transport. This is just telling us how spinors transform under Lorentz transformations, under small Lorentz transformations. And now all we have to do is say, well, okay, if that happens on curved space-time, and we have a parallel transport that generates an infinitesimal Lorentz transformation, then it should do this to the spinors. So we apply that to general relativity. Now, if E mu is a vector that is infinitesimally parallel transported in the direction of some tangent vector EA, then we know that it obtains an infinitesimal rotation, infinitesimal Lorentz transformation, which is simply given by this. This is the infinitesimal Lorentz transformation, where, remember, this is the connection 1 form. Infinitesimally Lorentz transformation valued 1 form. Now, the way we express this then is that we say that for a vector, we soon do it for a spinor. For a vector, we have that the vector transforms under infinitesimal parallel transport into itself, plus this little bit of a rotation, of a Lorentz rotation acting on that vector. And so this is to say that the affine connection of a vector in this direction is given by that expression. It's really a little repetitive, but I want to highlight the similarity to what we now do for spinors. So now when a spinor field SI is infinitesimally parallel transported in the direction of EA, we want that Lorentz transformation to do the trick. This Lorentz transformation. And so we say that the spinor field is going into the spinor field minus a quarter, and then the usual special relativity formula with the commutator of the gamma matrices, and now this infinitesimal Lorentz transformation is the infinitesimal Lorentz transformation that also applies to tangent vectors, cotangent vectors, and tensors in general. Now, let's clean this up. Under infinitesimal parallel transport, then, we have that the spinor field goes into the spinor field plus whatever the affine connection does to a spinor field when parallel transported in the direction EA. Now, from this, we should be able to read off what the affine connection is when applied to a spinor field. Namely, simply by comparing the two equations, we read off that the covariant derivative of a spinor field in the direction of EA is given by the infinitesimal Lorentz transformation acting on that matrix here. Oh, I thought it's plugged in. I hope that this will last until the break. Okay. All right. Okay, so for general Dirac spinors, so this is how the covariant derivative acts on a basis vector in the space of spinors. A general spinor is a linear combination, is a position-dependent linear combination of the basis spinors, and then we can apply the Leibniz rule for the affine connection to obtain that the affine connection acting on an arbitrary spinor is given by the affine connection acting on the product of the coefficient functions times the basis spinors. And here we have again, by the Leibniz rule, we have that the affine connection acts on the first factor in this, leaving the basis vectors the same, plus leaving the coefficient functions the same, and then acting on those basis vectors. We know how these things act, and we know how that is acting, because these are just coefficient functions, so the affine connection will just ordinarily differentiate them, and this we just figured out. So it's this. Therefore, we obtain that the affine connection applied to a spinor is given by this expression here. This is the application of the covariant derivative on coefficient functions. Remember that coefficient functions are just number-valued functions. And when you covariantly differentiate a number-valued function, it's just the ordinary differentiation of a number-valued function. And the ordinary differentiation of a number-valued function, well, what is that? It's a vector field applied to the ordinary function, and that is what we have here. And then this term here gets all of that. So that is the covariant derivative of an arbitrary spinor field, and that is what we need to write down the Dirac equation. So what we obtain is that the general relativistic Dirac equation takes simply this form, which is nice and easy to write down, but it's a little complicated when you write it down explicitly, because this expression is a little lengthy here, and that is what goes into this. If we spell it out, then this is what it is. So this is how curvature acts on spinors.
The affine connection is independent of the component of the spinor itself, right? Because each component is not necessarily related to, because we're used to all our vectors being directions in space, but here it's not a basis for directions in space, it's a basis for the
yes.
You have the I, it wasn't contracted with anything from the affine connection.
The I?
Well, you're
no, that's just a complex I here.
Above.
But can we postpone it to the break, because I'm worried we might run out of power here.
Sure.
Okay. All right. So this is actually the last slide. So this takes this explicit form. Now we did it in this pedestrian way, so that you see, the details of it. Now it turns out that there is another way to define a Dirac operator in curved space, which is much easier, but much more abstract too. Namely, we can also define a Dirac operator to be simply the exterior plus the co-derivative. Much simpler than that, right? Now, what would be the connection here? See, square that operator. If you square this operator, you get a d squared that goes away, you get a del squared that goes away, but you also get a d del plus a del d, which is the Laplacian. Right? So the square of it is then the Laplacian. But how do you identify then what it's actually acting on? Well, it's technically acting, of course, on the space of tensors. Actually, on the space of linear combinations of tensors. It's really acting on the Grassmann algebra, the exterior algebra, but most naturally not equipped with a wedge product, but with a different product. The product that ultimately has to do with the anti-commutation relations of the gammas. You get a so-called Clifford algebra. And that's something that you may want to work into your essay if you want. How does curvature manifest itself? All right. Okay, I guess we all deserve a good break now.